speaker is Aditya Chowdhury, and he will be talking about 21 centimeter emission from Galaxies as Redshift 1. Aditya, please go ahead.
Yeah, can you hear me?
Yes, Aditya, we can hear you.
Yeah, thanks, Steve. So I'll talk to you about H1 21 centimeter emission from galaxies at redshifts of 1. This work is primarily done with Nassim Kanikar and Jairam Chengalur. Here's the broad outline of what I'll talk to you about. I'll first give you an introduction and tell you why it is absolutely key to probe H1 in high redshift galaxies for our understanding of galaxy evolution. I'll tell you about our recently completed upgraded GMRT H1 21 centimeter survey of the deep 2 fields with which we have obtained for the first time a detection of the 21 centimeter line in emission at redshifts of 1. Uh, and then I'll talk to you about some very preliminary and recent results, the H1 scaling relations, redshift evolution of H1 mass, and then I'm not sure what's happening on the screen. 1 second. Yeah, I'll just go on. And then I'll talk to you about future plans and then touch upon how high Z H1 21 centimeter studies will look like with next generation telescopes, and then summarize the talk. Just as an introduction, what I'm showing here is all that sort of a key plot of what we have learned from optical and infrared studies over the last 3 decades or so. And what we understand now is that the star formation rate density evolves with redshift in the following way, that after beyond the epoch from the end of the epoch of reionization out to about redshifts of 3, the star formation rate slowly goes up, and this you can vaguely understand as galaxy formation taking place, as collapse happening, and then that triggering star formation in galaxies. And then there is sort of this plateau between redshifts of 3 and 1. And then beyond that, from redshifts of 1 out to the local universe, there's this very rapid decline over the next 8 gigayears or so in the star formation rate density of the universe. And this is by about an order of magnitude. And so it has been puzzling for a really long time now, that why is there this decline after this so-called the epoch of galaxy assembly, uh, which is this plateau region that you see from redshifts of 3 to 1, where about 50% of the stellar mass that we see in the universe have been formed. And in order to understand why this is happening, you have to probe the fuel for star formation, that is the cold gas in high redshift galaxies. And of course, atomic hydrogen is the primary fuel for star formation, which converts to molecular hydrogen and finally to stars. And so you have to understand how atomic hydrogen is evolving as a function of redshift in star forming galaxies. And to do this, the 21 centimeter transition is an excellent probe because you get MH1 directly from the emission signal because it's optically thin, and the differential between the state, the temperature is the spin temperature is the difference in the temperature of the two states is very low. But the problem is that this also makes it a very weak transition. And so there has been these very large integrations with some of the best telescopes we have today. The Arecibo, which sadly we lost a few months back, the WSRT, the JVLA, and the GMRT to push 21 centimeter studies out to redshifts of zero point 0.4, which have been incredibly hard. You have to spend hundreds to thousands of hours with these cutting edge telescopes to get detections of the 21 centimeter line at these intermediate redshifts. And so with these, the highest redshift detection that we have from an individual galaxy is at redshifts of 0.376, and a fairly massive galaxy with a mass of 3 times 10 to the power 10. Um, and so yes, I, I'm not sure why these are coming up on the screen, but I'll just go on. So in individual detections of 21 centimeter emission from even higher redshifts, say redshifts of 1, where very exciting stuff is happening with the star formation rate density, would be very challenging until next generation telescopes like expanded GMRT or the square kilometer array becomes operational. For example, today with the upgraded GMRT, which is one of if not the premier telescope to do such science, you'll need more than 10,000 hours of GMRT time to get an individual detection from a typical galaxy with 10 to the power 10 solar mass at redshifts of 1. And to get around this, you can use this technique, which is stacking or co-adding of 21 centimeter emission from a large ensemble of galaxies to find the average H1 content. And this has been successfully done out to redshifts of zero point 0.4 with the GMRT, in fact. And beyond that, Kaneker et al. 2016 made an attempt of this at the highest redshift to obtain upper limit, but this was with the legacy GMRT system. And it turns out the upgraded GMRT is, uh, uh, Deep, can you still see these lines on my screen?
Yeah, yes. I think
Yes.
So
you've
I'll
gone into
just
some annotation mode and that is why it's coming. But
uh,
ignore it for now. I don't think it's
I'll just stop the share and start.
yeah, maybe that may work.
Yeah, just try once.
Right, sorry for that. Let's see how it works now. Um, right, and so it turns out the upgraded GMRT is an excellent instrument to carry out such stacking experiments with its large bandwidth coverage. So what I'm showing you here is sort of the two highest frequency bands of the upgraded GMRT. There's another band below this, which I'm not showing here. And you can see that so in 3 bands, it covers the 21 centimeter line from the local universe all the way out to redshifts of 4. What I'll focus on here is a band 4 survey, which it covers this very interesting regime in the star formation rate density evolution, which is between redshifts of 0.74 and 1.45. So it sort of covers the peak of the star formation rate density and then the start of the decline. So a very interesting redshift range. Of course, for a stacking experiment, you need a galaxy redshift survey, because you'll stack the 21 centimeter spectra of galaxies with known positions and redshifts. And it is absolutely important that you have redshifts which are very accurate. So spectroscopic redshifts and very good spectroscopic redshifts. What we have used is a deep to survey, which is perfect for our purpose. This is a large survey. It's 99 with the DMOS spectrograph on Keck, and it covers the redshift range 0.74 to 1.45, which is exactly the redshift coverage of the band 4 receiver system for the 21 centimeter line. And the velocity accuracy for these redshifts are about 55 kilometers per second, which is also excellent for stacking. And so there are these 7 deep to subfields, and you can see overlaid on them in red the GMRT primary beam and the pointings that we finally chose. And in color is shown the number of star forming galaxies in each of these pointings that we cover with the GMRT. And so we have taken 520 hours of time with the upgraded GMRT. And so we split that 75 hours on each of these pointings. And we had, before doing the full survey, we had done a pilot in October, December 2018, which was just on these 5 fields, deep to 3 and deep to 4. And this was 20 hours per pointing. And this was published late last year. So this would be results that some of you might have seen. So I'll first present that, and then of course I'll move on to the results from the full survey, which we now have, and so that I can make some connection between what you might have already seen and what we have now. We had about 7,653 usable blue star forming galaxies, which we stacked over the 5 fields, which is 1.2 square degrees in size. And what we obtain is a clear detection of the 21 centimeter line in emission at redshifts of 1. And you can see on the left the 21 centimeter spectrum, the stacked spectrum of these 7,653 galaxies, and a signal which is clearly centered at 0. And on the right, what I'm showing you is the image plane stack. So I take the central region of the signal and produce an image, because the GMRT is an interferometer and you can do that. And you can also see that a clear localization at the center of the image for this detection. And the beam on the scale is 60 kpc. So we find that 60 kpc seems to be the typical size of these galaxies. And with this, we get an average H1 mass of 11.9 times 10 to the power 9 solar masses. And what we found was that the H1 mass was comparable to the stellar mass, the average stellar mass of these galaxies, which is actually very different from local universe galaxies, as I'll come to shortly again. And the other thing we found was that the H1 depletion timescale, the amount of time that in a quiescent picture that the H1 can sustain the star formation rate, is a 1 to 2 gigayear, which is very short. And uh, we, we propose that presumably a lack of accretion of H1 into galaxies caused the decline in the star formation rate density that you see. Of course, now we have
Aditya, you have 2 minutes.
yeah, okay, thanks. Of course, now we have the full survey results, and you can see from the 100 hours to the 520 hours, the signal has improved dramatically. The noise has gone down beautifully as expected. And the H1 mass that we have now from this full survey is consistent with what we had from the pilot survey. But now the signal to noise ratio is enough for us to do very interesting things with it. For instance, we can now probe the so-called H1 scaling relations. We can see how the average H1 mass at redshift 1, this very exciting epoch, evolves as a function of the stellar mass, for instance. And this is what I'm showing here. I've broken our sample of galaxies into 3 stellar mass bins, spanning roughly 10 to the 9 to 10 to the 11 2 orders of magnitude in stellar mass. And for comparison, I've shown the Z equals 0 result in blue. And you can see that there is evidence for evolution in the H1 mass versus stellar mass relation, specifically that at all these 3 stellar mass bins, the H1 mass is more than what you'll expect for the given stellar mass at the local universe, for local universe galaxies. And so at all stellar masses, it seems these galaxies have more H1 mass. The slope seems to be a bit flatter, but it's still consistent with within uncertainties with the slope of the local universe relation. What is perhaps more interesting is if I take this and then divide this by the star formation rate to find the H1 depletion timescale in the 3 stellar mass bins, and you can see that the depletion timescale of the least massive galaxy is about 2 gigayears, whereas for the highest mass galaxies, it's 0.7 gigayears, 0.6 gigayears, and that is surprisingly low. I mean, it just means that in 0.6 gigayears, if there is no accretion, the star formation rate will drop like a rock. And what is interesting is that this connects to what we know from optical studies about these galaxies. We know that the decline of star formation rate density that you see at redshifts less than 1 is primarily due to these galaxies. Uh, 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 and we also find sort of a direct evidence that there is a lack of accretion of H1. So we also could, of course, split the whole redshift range into 2 bins, and we just chose 2 bins so that one covers the epoch of galaxy assembly and the other the decline. And you see the spectacular drop in the H1 mass to the stellar mass ratio. It seems like from above redshift 1.2, the H1 mass to stellar mass ratio is very high, about 1.5, and all of this is at a fixed stellar mass, and then it drops very sharply and sort of stays constant at out to redshifts of 0. And so this tells us right away that something very special is happening in this redshift range, this very narrow redshift range. And one wonders what sort of things is happening. One speculation would be that there is some sort of a switching off of cold mode accretion in these massive galaxies, or that there is a feedback mechanism that is making all of this happen. That brings me to the future plan. And so, of course, we We'll explore the dependency of MH1 on other parameters, on environment, on star formation rate, and so on. And then we have also proposed even deeper observations to carry out a very detailed characterization of H1 at Z approximately 1. So we have proposed 580 hours in the upcoming cycle. And then perhaps even more exciting stuff, you would remember that GMRT also has a low frequency receiver, which covers redshift range from 2 to 3, 2 to 4 actually, but we will do a survey from 2 to 3. And we have gotten 200 hours to do start doing this survey at redshifts out to 3. And so with the GMRT, we'll soon have a picture of what is happening to H1 in galaxies over the past 11 giga years, which is very, very exciting. And finally, I'll connect this to what we expect from the next generation telescopes like the expanded GMRT and SK. Like I said, with current generation telescope, it is very, very difficult and very expensive in observing time to get even a handful of detections, forget a statistically large sample. But the expanded GMRT and the SKA would do, it will give us thousands of individual galaxies, as you can see in this plot, out to redshifts of 1.5. And and this in fact is one of the key science drivers for the square kilometer array, right from its inception, that you want to understand galaxy evolution by getting these large number of individual detections of the 21 centimeter line out to redshifts of 1.5. So to quickly summarize, we have now obtained the first detection of 21 centimeter line in emission at redshifts of 1, and we are sort of starting just very preliminary things that I've shown you today to carry out a detailed characterization of H1 in galaxies at these redshifts, and soon we'll push to even higher redshifts with the upgraded GMRT. Thank you.
Yeah, thank you, Aditya. So maybe we can take a quick question if there is one. So people who are on Zoom, you can raise your hand. So, okay. So Aditya, let me ask a quick one. So at the time of the square kilometer array, I mean, what will be the kind of companion optical survey which will work in this case?
So for the square kilometer array, you don't necessarily need a background optical survey to begin with, because you can do blind surveys. You will get individual detections from such telescopes. But of course, by that time, Subaru would be carrying out these amazing surveys with its new spectrograph, a multi-slit spectrograph, which would come online in a couple of years. And that would give us exquisite redshifts over very, very large regions of the sky, something that has not been possible very easily now with current generation optical telescopes. Like with Keck, for example, you had to spend 90 nights on the telescope to complete the survey, and that was 2 square degrees. And with the Subaru spectrograph coming online, you will be able to do tens of square degrees and have these very, very good redshift coverage.
Okay, thank you, Aditya. So